In this lecture, we are going to talk about interplanar spacing between HKL planes. So, this is a diagram that you see was what I had drawn towards the end of the last lecture. So, this diagram shows a set of parallel planes which have indices HKL. So, as I had said in the last class, when I refer to an HKL plane in a lattice or a crystal, there is a set of parallel planes which are equally spaced, and this diagram shows the spacing between the HKL planes. Now, here if I look at it, there is a vector, normal vector that is drawn, which is perpendicular to all the three planes that I have drawn, but of course, there is an infinite set of such planes, and they are equally spaced, and that spacing is what is called as the interplanar spacing, also referred to as symbolically as DHKL. So, this is the interplanar spacing for a specific set of HKL planes. So, we want to look at, or maybe let us look at one more diagram just to clarify things a bit, which is, let us take a specific set of HKL planes to understand this concept clearly. So, I am just drawing a set of unit cells, and this unit cell can be from any one of the Bravais lattices. So, for instance, I have this set of planes or this set of unit cells, and this is my x, y and the z axis. Now, in this set of x, y, this is indicated that which is the x direction, which is the y direction and which is the z direction. Let me consider the HKL planes 0, 1, 0. So, all of these form 0, 1, 0 plane, because this is my a axis, this is my direction of my b axis, and this is the c axis. So, 0, 1, 0 HKL planes, all of them are there, and they are all equally spaced. And what is their spacing? In this specific case, their spacing is b. Similarly, I can have a set of HKL planes in a more general way that I have drawn here, could be any set of HKL planes. Again, you can figure out what would be the normal. Normal is of course the b axis, in this case to the 0, 1, 0 planes. Now, what I intend to do is I intend to derive a relationship for what should be the interplanar spacing for some HKL plane. Now, generally for cubic system it is the simplest, and as we move away from the cubic system, the relationship becomes more complex, and for the most general case, which is a triclinic crystal, the spacing is the most complicated and very difficult to derive through normal geometrical tools. So, first what we are going to look at is how to derive the interplanar spacing for those lattices whose unit cells have axes which are orthogonal to each other, perpendicular to each other. So, let us consider the orthorhombic crystal. So, for an orthorhombic unit cell, we know that it would have A equals B equals C, and all the angles are going to be 90 degrees. So, let us look at this example. So, let me first draw a diagram with the HKL plane which is closest to the origin, because then all I have to do is drop a perpendicular from the origin onto that plane, and the perpendicular distance from the origin to the HKL plane would become the interplanar spacing. Now, this is some HKL plane whose Miller indices are HKL. Now, this HKL plane will be intersecting the x axis, y axis and z axis at along the x axis it will intersect at A by H, along the y axis it will intersect at B by K, and along the z axis it is going to intersect at C by L. And let me make a slight correction, since this is an orthorhombic system, A need not be equal to B, need not be equal to C. So, in the general case when they are unequal, we are going to derive a relationship for the interplanar spacing. So, now consider drop a perpendicular from the origin. So, let me just label this. So, origin is O, the perpendicular meets the plane at N, and let me also join a few more points. So, let me also say that these intersection points are A, B and C. So, let me draw a line from A to N. So, I have this triangle OAN, but first of all, since ON is perpendicular to the plane HKL, any line on that plane would also be perpendicular to it. So, let us write this: ON is perpendicular to plane HKL, that is the way I have drawn that, and I need to find basically the length of ON, which will give me the interplanar spacing. So, I can say ON vector is perpendicular to the plane HKL. The magnitude of this vector ON, which I will simply write it as ON. So, whenever I do not put a bar, I mean its magnitude. This is equal to the interplanar spacing of this particular HKL plane. Now, as I said, since it is perpendicular to the HKL plane, any line on the plane would also be perpendicular to the vector ON. So, which means that ON, so if I choose, let us say, the vector AB and the vectors, let us say BC. So, vector ON is perpendicular to vector AB and vector ON is also perpendicular to vector BC, and in fact, any other line I draw, for example, it will also be perpendicular to the line AC, but I just need to consider only two lines, because or two vectors in the plane, two vectors completely define the plane. So, let us look at now a few other vectors. For example, let me consider the vector OA. Now, the vector OA is along the x axis, and let me also define three unit vectors along the axes x, y and z, and these unit vectors are I1, along x, I2 along y, I3 unit vector along z. Normally, it's general practice to use IJK, but I am not choosing those symbols because then it gets confused with the symbols in the plane with the indices HKL. So, OA, what is the vector OA in now in terms of the HKL indices? Very clearly, it should be A by H, which is its magnitude, multiplied by the unit vector I1. Similarly, OB is B by K times I2, and vector OC is C by L times the unit vector I3. Now, what are the vectors AB and BC? So, let us first consider vector AB. So, the vector AB, if I look at it, to go from point A to point B, I can go along the vector AO and then along the vector OB, which means I can write AB as the sum of these two vectors AO plus OB. Now, I know what is the magnitude of OA, which is A upon HI1. So, what will be the magnitude for AO, or what will be the vector AO? It will just be minus OA. So, this becomes minus OA plus OB, which gives me the vector AB as minus A by H I1 plus OB vector plus B by K I2. Similarly, if I take the vector BC, now what is the vector BC? This is sum of the vectors BO plus OC. They take me to the point from B to C, which would be as before minus OB plus OC, and I know what is OB. So, that is minus B by K I2 unit vector plus C by L I3 unit vectors. Now, let us look at the vector ON itself. Now, the direction of vector ON can be defined by three angles which are called as the direction cosines. So, angle alpha 1 that the vector ON makes with the vector OA, similarly or with the x axis, ON makes an angle beta. So, let me just call that first one not alpha 1, but just alpha. ON makes an angle with the y axis as beta, and the vector ON makes an angle with the z axis as gamma. So, basically my cos alpha, cos beta, cos gamma become the direction cosines. So, let us try to write an expression for cos alpha. Now, remember the triangle cos alpha is nothing but the vector ON upon, so OA is the hypotenuse and the 90-degree angle that is made is the angle ONA. Therefore, cos alpha is nothing but ON upon OA, but we know that ON is DHKL and OA is nothing but A by H. Hence, this becomes H upon A times DHKL. Now, similarly, I can write for cos beta. For cos beta, what I will have to do is, I draw a line from B to N and form another right angle triangle, and I will simply be able to write for cos beta as K upon B times DHKL. So, now I have cos beta, and analogously cos gamma is going to be L upon C times the interplanar spacing DHKL. Now, I have this. Now, I write down one of the properties of the direction cosines, which is that cos square alpha plus cos square beta plus cos square gamma equals 1. I substitute for cos alpha, cos beta, cos gamma in this, and I will get h square upon a square times DHKL plus k square upon b square times DHKL plus L square upon C square times DHKL, and this sum is equal to 1. Rearranging the terms, in fact, the dH will also be squared. Rearranging the terms, I get 1 upon d square HKL equals h square upon a square plus k square upon b square plus L square upon c square. So, this is one expression that I have got for interplanar spacing for the orthorhombic unit cell. Now, it is easy to see that what will be the expression for tetragonal. One upon d square is equal to h square plus k square upon a square plus L square upon c square, because here you have a equals b not equal to c. So, and angles are still 90 degrees, and for the cubic case, which is the simplest, where you have a equals b equals c, I have 1 upon d square HKL equals h square plus k square plus L square upon a square. Now, for other systems like rhombohedral, hexagonal, or things like triclinic, monoclinic, where you also have non-orthogonal angles, then there will be some alpha, beta, gamma terms also coming in. In fact, in the case of triclinic, all the 6 parameters will come in the interplanar spacing. Difficult to derive the way I have been able to derive for the orthogonal case. For the interplanar spacing in those systems, we can take the result of what is called as the reciprocal lattice concept, and that concept will be introduced in the X-ray diffraction part of the course. At that time, we will see how to derive those interplanar spacings.